So 5.2 is really just going to be an example of how we can analyze the graph of a polynomial function. And the process is broken down into a multitude of steps. But what's really cool about it is that we really fuse together everything up to this point, all of the stuff from section 5.1, in addition to some of the things from chapter 3, like increasing, decreasing, maximums and minimums, domain and range. So we're throwing everything we got when we analyze the graph of a polynomial function. So there's going to be a little more interaction with this because I'm going to set up some parts for you and have you work on them independently, just to see, how successful you are in tying in, our most recent concepts, and then, just with a refreshing yourselves on some of the older stuff from things like chapter 3. So that's really all section 5.2 is about, is just, following a step-by-step process in which we apply all of our skills in order to come up with an accurate sketch of a polynomial function's graph. So the function we're going to be working with throughout this section is x squared times x plus 2 times x minus 2. And that's a partially factored form version of the polynomial. And for step 1, they want us to determine the end behavior of the function's graph. And keep in mind that end behavior is based on the leading term, a sub n x to the n. With the polynomial in partially factored form, it's not really evident as to what the leading term is. We would be able to identify the leading term if the function were written in standard form. So my mission for you is to take these factors and FOIL them all out. Okay, so I'm going to have you work on that for the next 30 seconds or so. Go ahead and FOIL out x squared to these two factors, x plus 2, x minus 2. And as a tip, you might want to do these first. All right, I'll show you what I got. That's x squared. And then when you FOIL these, you'll get x squared minus 4. And then distributing x squared in to clear parentheses, we arrive at the standard form version of this polynomial, x to the 4th minus 4x squared. So very good. So with the polynomial in this form, we have clear evidence as to what the leading term is. Okay, so I'm going to say a sub n x to the n corresponds to x to the 4th. And I'm going to add a little more detail to this x to the 4th. I'm going to put the coefficient of 1 in front of it. And keep in mind how we classify end behavior. We look at the degree. Okay, that's based on whether it's even or odd. In this case, 4 is even. And then we also look at the leading coefficient, but we don't look at it from an even-odd perspective. We look at it from a positive-negative perspective. And so this leading coefficient is positive. So we have an even degree and positive leading coefficient. The end behavior would be such that both ends point up. Okay, do you guys recall that from the table from the last section? All right. I'll include 1x to the fourth as well. Now for step 2, they want us to find the x and y intercepts. So I'm going to make a little workspace for each of those. And I'll show you how to start each of these. For x-intercepts, you're going to solve the equation f of x equals 0. And for a y-intercept, you plug 0 into the function. Now, I know we just went through all the hassle of finding the standard form version of f of x, but the factored form of it, or at least a partially factored form, is going to be a little more beneficial for something like this, in addition to step 3. So when you're solving f of x equals 0 for the x-intercepts, the more factored your polynomial function is, the better. It ends up leading to quicker math. And I'm actually going to split up x squared as x times x. All right, and we know that we would set each factor equal to 0 to solve for x. So we get a pair of x equals 0s. Negative 2 would be another answer for x, and so would positive 2. So in terms of intercepts, I'm going to write these as ordered pairs. 0, 0. I won't duplicate that ordered pair. Negative 2, 0, and 2, 0. What do we get when we plug 0 into the function? If you use the factored form, that'll be 0 squared times 0 plus 2 times 0 minus 2. What does this all turn into? 0. So the y-intercept coincides with the origin, which is one of our x-intercepts. Now step 3, we actually knocked out by doing some of step 2. It says determine the zeros of the function and their multiplicity, and then use the information to determine whether the graph crosses or touches the x-axis. So these are zeros. X equals 0, x equal negative 2, and x equal positive 2. And I'm going to list them out going vertically. We have 0, negative 2, and positive 2. And after each one of these values, I'd like to indicate the multiplicity. I usually separate it with a semicolon. Now, how many times did 0 show up as an answer? Showed up twice. So that would have a multiplicity of 2. I'll just write mult2 for short. Now, 2 happens to be an even number. And what did we just learn about zeros of even multiplicity? Do they cause the graph to touch or cross? So it would actually be a touch with an even multiplicity. With negative 2, negative 2 shows up as an answer only one time, so it's a multiplicity of 1. 1 is an odd number. So Isabel, you want to redeem yourself here? What's the graph going to do at -2? Going to touch or cross? Going to cross. You got it. Yep. So I'll say cross is x-axis. And then +2 shows up 1 time, multiplicity of 1. And as we just wrote down, the graph should cross the x-axis at that x-intercept. Okay. So step 4. Step 4 is helpful in that when we see the graph in our graphing calculator, we'll know how to connect all the points that we're figuring out throughout this process. So for step 4, in y1, we're going to enter x to the 4th minus 4x squared. So let's do that. So x, caret key 4, big minus sign, 4x squared. Now if you look at the coordinate plane in step 6, it goes from -5 to +5 on both axes. And so if we wanted to, we can adjust our window in the calculator to match with it. So you could go to the window, change the x min to -5, x max to +5, and then y min to -5 and y max to +5, and then hit graph. And to me, this kind of like resembles the root of a tooth. That's a whole tooth and nothing but the tooth, by the way. And you guys know what time is best to go see the dentist, right? 2:30. But anyhow, we can actually see some evidence of some of our results up to this point. For example, we have the x-intercept at -2, the graph is crossing. We have the x-intercept of the origin, which case the graph is touching, and then +2 is where the graph is crossing again. And then both ends are pointing up. So I know we're just about out of time here. So what I'll do is maybe ask you guys to wrap up the rest of these steps, and I'll include the solution on Blackboard. Let me just help you with step 5. Now, step 5 wants us to approximate the turning points of the graph. And keep in mind that turning points refer to the maximums and minimums. And going back to the graph, we have 2 minimums, and actually they're both the lowest point on the graph. So these would be absolute minimums. So you would use the calculate menu, option 3, to figure out the locations of those 2 minimums. And then the maximum, you would use option 4 in the calculate menu. Okay, so the turning points are really just asking you to find out the locations of the minimums and the maximum. And you know what? I'll just provide those to you. There's a local max, and that would be at the origin, 0, 0. But we have a couple of absolute minimums. And those are going to be at -1.41, comma -4, and +1.41, comma -4. So let's get the graph going, and then I'll leave 7 and 8 up to you folks, if that's all right. The local max at the origin, negative 1.41, negative 4. So about negative 1.5 if you want, and then go down by 4 units. And then go to the other side to plot the other absolute minimum. And then we have x-intercepts at negative 2, 0, and positive 2. And as we saw in our graphing calculator, it forms that sort of tooth-looking graph. And the graphing calculator really helps us to figure out how to connect all of these points. Right? And just a reminder that our end behavior corresponds to our result for step 1. The rest of this problem is just determining the domain and range, as well as the intervals of the x-axis where the graph is increasing and decreasing. Okay, so I'll have those answers up on Blackboard shortly after class if you want to check your work with mine. But do you guys have any questions for me before I dismiss you? You guys ready for that 30-minute nap? That was a lot of info today, all right? So, take some time to review everything that we went through today. If you need to rewatch any of the session, by all means do so. And if anything comes up, feel free to let me know.